When you're watching this video, this means I'm probably offline. So welcome to the backup video. My name is Lisa Meile and I'm a PhD student at the University of Erlangen-Nuremberg, which is in Bavaria. I've written a survey about network calculus results for time-sensitive networking, and I thought that this might be interesting as an introduction so that you can catch up with what is going on in our area. To make it clear, here the overview. At the beginning of my presentation, I will discuss queuing delays. Therefore, I present you TSN schedulers and their service curves in detail. This will take a little longer, but I think it's highly interesting, so stay tuned. This is the survey part, which you can also read in my paper. For some of the participants here, this is not new, of course, because they are the inventors of these results. And my task is only to provide an overview and the unified notation of all of the results, and then extend it, as announced, with hardware delays, and set them in relation with the queuing delay. And a highly interesting research area is the application delay, which we will then discuss as the third point, with arrival curves, application maximum, traffic, and interrupt latencies. And I will conclude with an overview and the effect which each of these delays has. So let's start with the queuing delay. As I'm recording this in advance, I can only guess. But I highly guess that Luxi Zhao presented time-sensitive networking before me absolutely well. So there's no need for me to go into details here. Just a short remark. Time-sensitive networking bases on Ethernet, and it is a set of standards which enable the network to offer real-time guarantees, for which we are using network calculus, of course. Generally, we have up to 8 queues in an output port of a TSN forwarding device, and each queue has one priority. After the queue, different scheduling mechanisms can be implemented. The most simple, which is not used commonly in TSN, would be strict priority. But of course, there are various other schedulers. The first one who made it to the standards is called Creditbased Shaper. We will talk about the details of all of them soon. Then we have a relatively new one called asynchronous traffic shaping, and the most often used one, I guess, in practice, the time-aware shaper. Besides, we can also combine them to make things a little more complicated. This table here might overwhelm you a little. You do not need to look into the details here. I just want to show you what the main part of my survey is. For each work, I have provided the source, of course, and the mechanisms for which they derive their results. As you see, I have shortcuts, for example, the combination of TAS and CBS. And this can also be differently abbreviated in each literature. There's an own way to do this, so maybe we have time to talk about this later if I'm online again. Then I have provided how do they base on each other, which effects do they consider, like preemption or the impact of a certain control data traffic, and which curves have they derived. And I will present you the minimum service curve for each of the mechanisms to give you a rough idea how the different results depend on each other. Thereby I tried to make the results as visually as possible and introduce a notation in which you can see the relationships between the curves the best. We start with the credit-based shaper, assuming that we have 2 credit-based shaper queues, one for priority 1 and one for priority 2. To illustrate the behavior, here the credits of each queue is mapped. Blue for priority 2, red for priority 1. If we assume that a frame of priority 1 arrives directly at time tier T0, then the transmission would start, of course, and the credit of the queue would decrease according to a so-called send slope, which is the rate by which the credit decreases. So, of course, the credit at the end of the transmission is then the time of the transmission times the rate by which it decreased. If we now assume that another priority 1 and a priority 2 frame also arrive, then at this point here, the priority 2 queue would also want to start sending, but it cannot since the link is busy, so it needs to wait. And while waiting, a queue credit will increase by a so-called idle slope rate. At the end of the transmission, we would assume that since we have another priority 1 frame in the queue, for strict priority schemes, this frame would start first. But this is not true for Credit-Based Shaper. For Credit-Based Shaper, only queues with a positive credit can start transmission. So the Q2 is allowed to send, thus its credit will decrease, the credit of Q1 will increase. And as you can see here, transmission of Q2 is finished and we have another priority 1 frame in the queue, but we cannot send since the credit of the Q1 is not positive or equal to 0 yet. So we have an idle time and then the Q1 can send again. The minimum service curve for Credit-Based Shaper depends on 2 parameters in principle, the credit and the idle slope. The idle slope is chosen so that it presents the reserved bandwidth of the queue. The send slope is then defined accordingly. Therefore, the service curve simply looks like this. The long-term sending rate is of course the idle slope, as it is defined like that. And our initial delay is the time until we reached the worst case credit. So we have a rate latency curve. And we now simply need to find out what is the worst case credit. So for Q1, this is simple. Of course, in the worst case, when we want to start our transmission, it might happen that another queue, which has a priority which is lower than 1, starts its transmission, and in the worst case, it has the maximum possible packet length of the queues which have a lower priority. Until this point, our credit will increase, and after that, there's nothing that can stop us, so we can start our transmission. The value here is thus simply the duration for the sending times the idle slope, and the duration is of course just the packet rate, the packet size divided by the link rate. For priority 2, this is similar. Of course, at the beginning, a packet which has a lower priority than priority 2 can start. And then, in this case, priority 1 would be preferred. So we would need to wait and be idle until the priority 1 has finished its transmission. So in the worst case here now, the priority 1 queue has a credit of 0, so it can just now start one more sending. And of course, in the worst case, this would be the maximum packet size which Q1 has, and only after this we can now start sending. So the delay for this is simply that another packet sends, then that the maximum packet of priority 1 sends, and the duration which it takes for priority 1 to decrease its credit from the maximum value to 0. And it decreases by the sending slope, so this is the time which is illustrated here. Actually, this service curve can be improved, since of course we do not send constantly with the idle slope rate. But if we can start our transmission, we send it with the full link speed. And then would need to wait until we can send again. This idea here, and also how much effect it will have, will be discussed later by Mohammadpour. Now that we understand the basic credit-based shaper, we can use this curve to model various other scenarios. The first one which we can take a look at is what happens if the so-called control data traffic is needed in the network. This is simply a higher prioritized queue than our credit-based shaper queues. So, to model the network calculus curves for our credit-based shaper, of course we need to subtract the time while the control data traffic queue sends, since the credit-based shaper queues cannot send during this time. So we will adapt our service curve and simply subtract the time for which the control data traffic sends from our sending time. What is the time that the control data traffic sends? This is determined by the output of the control data traffic queue and the link rate, since of course the output divided by the link rate is the duration for which it takes to transmit the output. And how can we get this output? Here we use basic network calculus results. And as proposed by Muhammadpur, we can get the network calculus output by defining a arrival curve and a service curve for the control data traffic. And since this is strict parity and has the highest priority, the control data traffic service curve has the link rate and an initial delay of one other queue finishing its transmission. And the result will then simply look like a decreased service curve. So this is the relation between the credit-based shaper curve and the credit-based shaper curve if we have higher prioritized queues. Another way to reuse our credit-based shaper network calculus curves is in combination with the so-called time-aware shaper. So we have time intervals during which the gates are closed, so we cannot send, and also guard bands as explained by Zhao. We need to subtract the time for which the gates are closed and the guard band from our sending time again. So again, we can simply reuse the credit-based shaper curve and subtract the gate closing and guard band time, and how this time was extracted. This has been explained by Zhao before. This will then be how the new service curve for TAS will look like. So, our last shaper for today is the asynchronous traffic shaping, which is currently in draft version for TSN. It implements so-called interleaved regulator queues before the normal queues, where packets of different priorities can bypass each other's. We do not need to go into the details here, you can look up the sources as always, but the main result is that interleaved regulators come for free for the overall worst case delay of all flows, meaning for the class-based delay, which is the only delay which we are talking about currently. So, our service curve for the combination of asynchronous traffic shaping and CBS is not different from our normal credit-based shaper service curve. The literature also considered the effect of link shaping, which I highlighted in my survey with and link or including link. And also they derived strict and shaping curves for the credit-based shaper and the credit-based shaper in combination with TAS, as you see in this line here. These two curves are derived by assuming that the credit at the time t0 is not 0, as we assumed it for the minimum service curve before, but has either the maximum or the minimum value correspondingly. The shaping curve is non-greedy, which means that we can upper bound our output with it, which is quite nice. As announced before, we need to take care that all results are class-based, and to get flow-based results, we need to define the residual service curve. Since we have minimum service curves which are defined for the single queues, these are FIFO systems, so the strictness of the service curve is not required. But this has not been investigated any further currently, so this can be a nice research topic for the future. Also, we need to take care that in asynchronous traffic shaping, of course, the class-based delay does not change, but the per-flow delay might be influenced with the interleaved regulators. In the second part of my presentation, I will speak about hardware delays. Why do I do this? Well, most often we simply neglect all other delays than the queuing delay, which we discussed before. But the problem is that we are the community who derives worst-case guarantees for packet latencies. So we should be definitely aware about how big is the influence of hardware delays, for example in TSN. So to start with, the simplest delay, of course, is the propagation delay. It is just how long does it take for one bit to travel the whole cable. And in our case, we have an Ethernet cable, so we have a fixed propagation speed. We have a maximum cable length, of course, and so we can simply multiply these two and see that the worst case propagation delay is about 0.5 microseconds. Another delay, which is often forgotten, is called transmission delay. After the propagation delay, only one bit arrives. The transmission delay tells us when does the whole packet arrives. We need to wait until the serialized packet has completely arrived. In network calculus, this can be modeled with a packetizer, but it has not been discussed before in network calculus, so we need to be aware that all service curves, which we discussed before, need to be decreased by the maximum packet size, as this is how packetizers influence the service curves. Of course, this is only true for the so-called store and forward mechanism, where the whole packet needs to be read first before it is processed. If we use cut-through, which is also possible in TSN, then this would be improved, and we would only need to subtract the length of the header. A delay which is mostly completely neglected in our works is the processing delay of the forwarding devices. Only few works deal with them, and to the best of our knowledge, we have only one work which proposes estimations for this time. So to get estimations for all of these results, we can use the estimation of Ramaswamy. And for the processor clock frequency, we use the actual frequency of a real TSN switch. So if we set in these values, we will end up with a processing delay of 7.4 microseconds, which highly depends on the memory lookup and might be too pessimistic for modern devices, but it is definitely an upper bound. These were all the hardware delays that can occur, and now we consider a completely different kind of delay, the application delay. Why do we need to do this? If a fire alarm is triggered, then we want as soon as possible a reaction, of course. But we also need to consider how long is our delay from when the alarm is generated until it goes on the link. And then if this is too long, we might need to decrease our deadline requirements for the network, of course. And also on the receiver, before we can do something about the fire, we need to process this first. So, what are estimations for these times? First of all, how applications are created and configured in TSN is an open research question, which we are also currently working on our chair. And here in this presentation, I only want to highlight some possible scenarios and shortly discuss how their worst case delays could be investigated. I will go into details soon. First of all, generally, for guarantees, we need an upper bound on traffic that an application creates. If we do not have any upper bound, then we cannot derive any guarantees with deterministic network calculus. So we need, for example, an arrival curve of the application itself, and this can be derived, for example, by code analysis or observation measurements of the application itself, as has been done on our chair before. So if we send the traffic unshaped on the link, then the application will generate a packet and the sending will be a little bit afterwards. This a little bit afterwards is dependent on the interrupt latency. And this interrupt latency is highly variable. We can have estimations from literature which say that on normal Linux operating system, for bandwidth intensive tasks where they really put a lot of workload on the system, the worst case interrupt latency was 150 microseconds. Interestingly, this does not change too much for real-time Linux systems. The benefits of real-time Linux systems, according to this source, mostly applies on average interrupt delays. But be careful. These 140 microseconds were on a machine which had bandwidth-intensive tasks. If the machine also works on other tasks which are file-intensive, then this latency can increase up to 11 microseconds. But as we know, for example, from Fiedler, shaping traffic at the edges will decrease the overall end-to-end delay. If we use a time-triggered operating system, as proposed by Koppetz et al., but we would have an operating system which schedules the task and interrupt execution. So, in the worst case, our application, our fire alarm would be generated, and then it would need to wait a complete scheduling before the next interrupt is available for this application. But there are more things to consider here. Our packet here is delayed by the whole scheduling interval plus the time of the non-preemptive task. And it can even get more complex if the transmission does not finish before. At this level here, we can also experience queuing delay. So this context here is highly interesting. My colleague on the chair is working on this for optimal time-triggered communication. Last but not least, in the application delay, it might be possible that our sending device directly implements a TSN scheduler itself or orientates to a so-called class measurement interval. This thing here is defined in the standard as well, and it tells us that only a certain amount of packets can be sent during an interval. So, if we have this scenario, then we again need an interrupt, of course, but we will also need to handle our sending device as first hop. So we have the arrival curve of our application, and then we need to see, does our sending device has a normal task only with gates or a task with credit-based shaping. Use these service curves and get the network calculus delay for this as well to get the sending or the application delay. Here we want to highlight that for getting this delay, we would also need, for example, the service curve for asynchronous traffic shapers and the service curve for the class measurement interval. At the receiver, things are a little bit less complex. We will of course need to receive the packet, we will trigger an interrupt again, and we need to process the information. For the processing, we can assume that it is similarly quick as for the forwarding devices. This is just a rough idea. So, the delay at the receiver is the sum of these three. As you now got a lot of information, I will present you now the overview of all of them shortly and how much effect each of them has on the total end-to-end delay. So first of all, for a credit-based shaper for priority 2, using a 100 megabit per second link and the idle slopes provided here, we would experience a 720 microsecond queuing and scheduling delay. The transmission delay would be 120 microseconds, the propagation, of course, 0.5 microseconds, and the processing only 7.5. Assuming that we send unshaped traffic, which is less than if we would also implement a shaper here, we would have 150 microseconds at both applications, and of course the processing delay at the end again. So, to make this illustrative, we would have, for 100 megabit link with one hop, the queuing delay would make 60% of the end-to-end delay, the application delay would make 23%, and the hardware delay would still make 20% of our delay. So neglecting these without knowing this effect would not render any safe guarantees. If we increase the link rate to 1 gigabit per second, then the transmission delay would highly decrease, the queuing delay also. These delays look differently. In this case, for the 1 gigabit link, the hardware delay is indeed neglectable. The queuing delay, however, compared with the application delay, since the queuing delay decreases that far, the application delay makes a much higher amount of the total end-to-end delay. So, the future work, which considers these delays here, will be highly relevant for the topic as well. We have set up a small network with 2 switches and a perfect scheduler with no queuing delay at all, and use the 1 gigabit per second link as well. And in this case, the delay was never higher than 2.8 microseconds. So, as we can see, our estimations, which we get from literature and the theoretical analysis, only from sending to receiving, is pretty good. And the same is true for application to application, for which we measured up to 300 microseconds, which also sums up quite well to our theoretical analysis. And as I said, we will continue these researches in the future. And until then, I hope that you found some interesting points in my talk. And I'm really looking forward to speak with you in person.